Hi, everybody. So it's a pleasure for me to introduce Professor Mauro Paternostro for the talk today. And many of you certainly know Mauro, but it's now a kind of a tradition to have a formal presentation of the speaker. So Mauro Paternostro received the PhD in physics from Queen's University, Belfast, for his work on theoretical quantum information processing. After working as a research fellow at the Institute for Quantum Optics and Quantum Information at the University of Vienna and at Queen's, he was awarded in 2018 an EPSRC Career Acceleration Fellowship and appointed as lecturer at Queen's, then as reader in 2010, and then as full professor in 2013. Professor Paternostro is head of the School of Mathematics and Physics at Queen's and co-leads the university's quantum technology group, where he works on quantum information processes, quantum optics, and their foundations. He is strongly interested and has significantly contributed to non-equilibrium quantum thermodynamics, quantum optomechanics, and the coherent manipulation of open mesoscopic quantum systems. Honors include the Leverhulme Trust Early Career Fellowship and Alexander von Humboldt Fellowship for Experienced Researchers, and the Royal Society Wolfson Research Fellowship. He was the vice chair of the Cost-Action Quantum Technologies in Space. Mauro has attracted over 12,000 citations so far, and funded in excess of 20 million euros from a number of funding bodies, including the UK EPSRC, the EU FP7, the Royal Society, the Cost-Action, the Templeton Foundation, the Leverhulme Trust, Horizon 2020, and Horizon Europe. And now, I mean, after all this, Mauro, apologies, but I don't find anymore the announcement with the title of your talk. So if you can share the slides, and I will read it for you. Okay, so thank you. So today we'll talk about informational steady states and conditional entropy production in continuously monitored systems. So thank you, Mauro. The stage is yours.
Okay, thank you so much. Am I unmuted? Yes, I am unmuted. Thank you, Angelo, for the introduction. Thank you for the invitation. Thanks, Antimo, for organizing that. So can you see? Yeah, you can see my screen set. And yeah, I'm going to presentation mode, and hopefully it will work. So is it visible? Is it okay?
Yeah, it's perfect. We see the slides as
perfect. Perfect. Okay, so let's go through. Oops. Let's go through. Yes, perfect. Let's go through this presentation, which is indeed aimed at illustrating certain developments in the field of non-equilibrium quantum, say, thermodynamics of quantum processes and systems from an information theoretic viewpoint, which is precisely the context from which much of my research in this subject is performed. As Angelo briefly mentioned, the development of a framework for information thermodynamics is indeed a big topic of investigation in my group, and has taken a lot of my research effort in the last 5 to 10 years. And this is just say a summary of results that we achieved within my group, trying to build a framework for the description of non-equilibrium thermodynamics in quantum systems that are indeed continuously monitored. Okay, let's see which is the context where this discussion will will occur. I will start with a brief introduction to the formalism of so-called entropy production within the context of continuously measured quantum systems. The second part of the talk will address the emergence of and the definition of so-called informational steady states as the states that you achieve when subjecting your quantum system undergoing a quantum process to the competition between information loss due, for instance, to the interaction between your system and an environment surrounding it, and the information gain process that you achieve by the performance of suitable measurement on the system itself. And the third part of the talk it depends on how much I'm going to actually talk. But I hope that in the third part I will cover, I will be able to cover, I say, a theoretician viewpoint on a recent experiment that my group has been involved into, and aimed at indeed observe part of the results put forward in this theoretical framework that I hope to present in part 1 and part 2 of the talk. Okay, without further ado, let me start with by giving credit to the other legs of these endeavor. The endeavor of say, building a framework for information thermodynamics of continuously measured quantum systems. And the credit should be given to Alessio Belenchia, who is used to be a Marie Curie fellow in my group in Belfast and is now at the University of Tübingen. Luca Mancino, who was a postdoc in my group in Belfast, and Gabriel Landi from the University of Sao Paulo, with whom we have a long-standing collaboration on topics related to the points that I will raise today. And at the experimental level, instead, so whatever I will discuss aimed at illustrating experimental endeavors, well, my thanks go to Massimiliano Rossi and Albert Schlisse. They were both in Copenhagen when the work that I will present has been performed, and Massimiliano has meantime moved to ETH in Zurich. Massimiliano was working in the group of Albert Schlisse, who is one of the leading teams at the experimental level in the management, control, and manipulation of optomechanical devices worldwide. Okay, having given credit to the collaboration, let me present, say, the main ingredient of this discussion, which is entropy production, and why. So in a sense, you can take this slide as an invitation to address the topic of entropy production when dealing with non-equilibrium dynamics. And the reasons are manifold. The first motivation coming from the fact that, say, any non-equilibrium process inevitably dissipates energy, and by dissipating energy, these produces irreversible entropy, so generates a flux of irreversible entropy that affects the performance of the process itself. This is particularly important if, like me and part of the community interested in the non-equilibrium thermodynamics of quantum systems and processes, if you're interested in the performance of microscopic or nanoscopic machines. So the idea, part of the goals of the community interested in working in the non-equilibrium thermodynamics of quantum system is the engineer and realization of microscopic heat engines able to outperform classical counterparts in the management of the energetics of a working fluid. And by doing that, so doing that through the exploitation of quantum resources. Well, entropy production is indeed plays a key role in the identification, in the quantification of the performance of both classical, but particularly so quantum quantum engines in operating out of equilibrium. So the characterization of non-equilibrium of entropy production in non-equilibrium processes is indeed important at a very from a very pragmatic level as a key ingredient in the attempt at quantifying the performance and characterizing the performance of quantum nanoengines. And finally, the motivation that is probably the closest to my heart, this framework for the reversibility of quantum processes is a fantastic opportunity for the characterization of the quantum to classical transition. Systems that operate close to the boundary or the border between classical and quantum domain perform markedly differently in terms of the ability to and the capability to produce entropy and to give rise to entropy production. And therefore, any attempt at characterizing the production of entropy in non-equilibrium processes might be a very nice and a very exploitable Trojan horse to characterize the occurrence of the quantum to classical transition. And there are indeed results in this sense that we will be putting forward in the next few months in the year, within the context of the development of this framework for the characterization of thermodynamics of non-equilibrium quantum systems. Okay, going a little bit more towards the technical side of the discussion, let me start from the foundations. Okay, so the second law of thermodynamics, Clausius' statement on an uncompensated transformation that ascribes the exchange of heat, so energy, between a system and a reservoir at a temperature T, links it to a change in the entropy of the physical configuration associated with the physical configuration of your system. So any exchange of energy between system and environment is indeed associated with a change of the entropy of the state of the system itself. The second law in this integral form is very nice. It's as a fantastic tool to characterize the non-equilibrium processes, both classically and quantumly, but is not the most manageable or convenient form of the law itself. It is often the case that a differential version of it is used, built on the fact that you try and attempt at compensating left and right hand side of this inequality by introducing exactly entropy production. So entropy production in this context is indeed introduced as the quantity that allows you to translate Clausius' law from an inequality to an exact statement, an equality. And therefore is the uncompensated terms that allow you to balance, so to say, the income and expenditure relation, in a sense, between the change of entropy of the state of the system and the amount of energy that you exchange between that the system exchanges with the environment in the form of heat. As I was saying, the integral form is not necessarily the most convenient form to use. It is customary and indeed often the case that people make use of a differential form where the rate of change of entropy of the state of a given system is associated with these two quantities, pi of t and phi of t, which are defined as the entropy production rate and the entropy production flux, respectively, and that one can understand in a very rough, in a very intuitive manner through this stupid cartoon. So if I have my system interacting with its environment, with its reservoir at a temperature T, and the process is a process that takes my system out of its own equilibrium. So the system has initially been prepared in a state that is not at equilibrium with the environment. Then what I will be led to quantify by Clausius' law will be a process where intrinsically my system generates entropy at a rate pi of t, and a process where entropy leaves my system in a broad sense. So could be entropy that gets into my system. So it depends on the sign of phi, but with a flux rate that is characterized by phi of t. So as I was saying, pi and phi are very well defined roles in this game, and hopefully throughout this presentation, these two quantities will always be labeled as pi and phi for clarity of presentation. Okay, when you deal with quantum processes, the question that people try to answer is, what is the role that quantum fluctuations have on the quantification of entropy production, on basically on determining the production of entropy that results through a non-equilibrium process. And in addition to this fundamental question, what we are going to address is what happens when you add to the scenario that has been somehow depicted by the cartoon that I have here, also an extra ingredient embodied by the performance of measurements, which are key ingredient, so to say, in the paradigm of quantum mechanics, as we know. So the situation that we are going to address together in the next 30 minutes or so can be schematized as follows. So suppose that your system, which is here very inefficiently represented by this gray ball, in contact with a reservoir at a temperature T, and the interaction is this flash, yellow flash that you see there, has been prepared, the system has been prepared in a non-equilibrium state, or undergoes a non-equilibrium process that results in a rate of entropy production that I call pi. And here the subscript UC stands for unconditional. So this is the entropy production rate that you achieve through this non-equilibrium process if you let it occur as it is. So without any conditioning process, any conditional influence on the dynamics of the system itself. But what we want to do is to compare this pi you see, the rate of entropy, the rate of production of entropy in the unconditional case, with what you get when you perform a measurement on the system itself, when you actually inquire about the state of the system at various times, hopefully continuously, because that's what experiments can do in a relatively easy manner, and that will result in a different rate of entropy production, which is pi, and that is in general a different quantity than pi you see, than its unconditional counterpart. What we are going to do is to link the occurrence of, say, basically the difference between pi and pi unconditional to an information theoretic quantity that is related to explicitly to the amount of information that you acquire on the system through, or its dynamics, through the measurements that you perform on the system itself. Basically, what we are going to illustrate is how to relate the amount of information that a Maxwell demon acquires on the state of your system to the degree of irreversibility of the process that the system itself undergoes. Okay, in order to fix the ideas, let's study and address a specific situation. I'm a quantum optician by training. So being a quantum optician, I like to refer my paradigmatic system, so to say, to that of, say, to a situation that is typically occurring in quantum optics. So let's consider a particle, could be a trapped atom, a trapped ion, could be a levitated nanoparticle, any your favorite quantum system, so to say, trapped and embedded inside an optical cavity. And I will allow for the cavity to be pumped from the external world. Okay, so energy can leak into the cavity itself. And needless to say, if you let a pump leak into the cavity, then you have to allow for some noise to leak into as well and affect the dynamics of the object inside the cavity. I would also allow for processes of dissipation and decoherence to take place naturally in the dynamics, in the evolution of my system of interest. And because I'm explicitly assuming a leaky cavity, I will also allow for some signal to leak out of the cavity and reach a measuring device. Okay, so that's the ingredient, the extra ingredient that I'm going to plug into the framework for the characterization of non-equilibrium thermodynamics. And what I'm going to allow is, what I'm going to assume is that this measurement process is a continuous measurement. Okay, so maybe my detector acquires weekly information about the system itself, and I'm going to use it possibly to condition the dynamics of my quantum system through some feedback unit. Although in the following, I'm going to exclude explicitly the possibility of a feedback unit, while the results that I'm going to show are not necessarily invalidated by the absence of feedback. So while I'm not going to discuss explicitly the effect of feedback, the results that I'm going to show can be easily generalized to the case where you have a closed loop that takes information from the measurement device and brings it back, uses it to condition the subsequent dynamics of the system itself. Okay, Now, working assumption, and I preempt the question already. I'm going to relax the working assumption in the second part of this talk. Let's restrict the framework to quadratic evolution in the operators of my quantum system and Gaussian states and measurements. Okay, so in particular, what I'm going to assume is that I have an harmonic oscillator as a trapped particle. So this can be a particle trapped in a quadratic potential, for instance, in a parabolic potential. So an harmonic oscillator, a quantum harmonic oscillator that I'm prepared in a Gaussian state, whichever favorite Gaussian state you have, could be a squeeze state, a thermal state, a coherent state of motion. I'm going to perform an evolution or I'm going to assume that the system performs an evolution that is quadratic at most in the quadrature, in the position and momentum operator of my quantum harmonic oscillator. And I'm going to perform measurements that are Gaussian. So typically speaking, or say in general, a general dyne measurement like homodyne or heterodyne measurements, which are they have the advantage of being easily implementable in the experiments and are instrumental for the building up of the framework that I'm interested in presenting in this talk. Okay, that allows me to somehow to build a series of results of an explicit analytical nature. But as I said, these assumptions are not crucial. They can be relaxed, and this is what I'm going to do in the second part of the talk, and what has been done in this PRX quantum paper that has been recently published by myself, Alessio, and Gabriel, and where we provide a general framework for the analysis of systems adhering to this general situation. Okay. What am I actually facing? Which is the problem that I'm actually facing? If I exclude the feedback loop, what I have is that the state of my system, in light of the fact that I'm performing a continuous measurement process, undergoes a stochastic dynamics described by a stochastic master equation, where the deterministic, so to say, the unmonitored part of the dynamics is accounted for by this green box here, where I have the Hamiltonian of my system, the evolution induced by the Hamiltonian of the system, and also all the decoherence and dissipation mechanisms that affect the dynamics of the system itself. The noise affecting, affecting my dynamics, the dissipation and decoherence processes that I have explicitly allowed to affect the dynamics of the harmonic oscillator. The stochastic part of the evolution is all ascribed to, say, the measurement steps, where basically my general dyne measurement process acquires information, allows me to acquire information on the dynamics of the system at a rate eta k, and say acting back on the system itself through basically determining an overall stochastic evolution. Yeah, that's the description of the operatorial term that enters the stochastic term in the dynamics of my system, and where see appropriate operators of my system. Okay, what do we have? We have that in light of the fact that I'm restricting my dynamics to quadratic dynamics, quadratic evolution, Gaussian initial preparations, and Gaussian measurement, I can translate that stochastic master equation into an equation of motion for the covariances of my system only. So the variance of momentum and position and the correlations between these two quantities. Okay, so this information can be plugged together, can be summarized together very efficiently in the form of the so-called covariance matrix, which is the object sigma that I have in this equation. And if I do that, then I discover that the stochastic master equation that I've presented before can be translated into a fully deterministic equation of motion for the covariances of my system, and instead a stochastic dynamics for the first moments. So while the second moments of my evolution are fully deterministic, the first moment are not. And this is what I get by plugging in the general dyne measurement that I have allowed for in my dynamics, that will affect the dynamics, the evolution of sigma and x as follows. So with respect to the unconditional dynamics, the conditional dynamics of the covariance matrix will be subjected to modified parameters, but modified dynamical terms. Here, A and D are two matrices that account for the coherent dynamics, so the Hamiltonian dynamics, the noise affecting my system, but also the noise entering the cavity itself. And this is fully embedded into matrix D. Well, when I plug my measurement step, then the dynamics of the covariance matrix will be affected by new A, an A tilde, a D tilde, so a matrix of noise that is affected as well, and an extra term that is embedded, is encompassing altogether the effects of the measurement itself. I can recast this equation of motion entirely into, and ascribe it to the very same A and D that describes the unconditional dynamics, pushing the effect of the measurement all in this new matrix chi that indeed depends entirely on the measurement that I'm performing. On the other hand, when I look at the first measure, at the first moment, the evolution, the unconditional evolution, as I anticipated a few minutes ago, becomes an explicitly stochastic dynamics that depends explicitly on the measurement. Okay, so there is an extra term of an explicitly stochastic nature that depends entirely on the fact that I'm performing a measurement on the signal leaking out of the cavity. So the message to take home is that while variances and covariances evolve deterministically, yes, affected by the measurement, the first moment evolve stochastically. So the stochasticity is retained at the level of the first moment. And the splitting between covariances and first moments is entirely characteristic, is a feature of the quadratic nature of the evolution, the Gaussian nature of the evolution that I am considering. When I look at the rate of change of the entropy of my system as a result of the overall dynamics that I'm illustrating, then I can split in light of what in analogy with what I did with Clausius' equation of motion, with Clausius' law in the differential form. I can split it into a term that is reminding us of an entropy flux, and a term that is basically an entropy production rate. So this d phi and this sigma. Now, the change in entropy of my system depends entirely on the covariance matrix. And as the covariance matrix is deterministic, the change in entropy of my system has to be deterministic. While the two objects, so the entropy production flux and rate, depend instead also on the first moment. And depending on that, they are stochastic in nature. And in order to get rid of this stochasticity, what I'm going to do is to take ensemble averages of these quantities. And these are the rate of entropy production pi and the rate of entropy flux phi that I've illustrated before in my introductory slide on the entropy production in the context of Clausius' law. When I do that, so when I do this splitting, and doing a little bit of algebra based on the definitions that I have introduced, I've given, then you realize with very little effort that the rate of change of the entropy of the system is due entirely to a rate of change of entropy that is entirely unconditional. So it's this DSUC that I will get if I had not plugged in my measurement device, plus an extra term that is this I dot dt, that is an intrinsically information theoretical term, depending explicitly on the fact that I am performing a continuous measurement. In fact, an explicit expression for I dot can be gathered, and this is again owing to the quadratic nature, the special nature of the dynamics that I am considering, so the quadratic Gaussian nature, the Gaussian dynamics that I'm considering. So you can gather an expression for I dot that depends entirely on the covariance matrix sigma, on the noise matrix, the affecting the matrix that describes the noise affecting entering the system itself, but also on the matrix describing the measurement, chi. And whenever I don't perform a measurement, so I don't plug in my general dyne measurement device, and therefore chi is 0, as you can appreciate, the sigma, the conditional covariance matrix goes back to the unconditional one, and the two terms that enter the expression for I dot cancel explicitly, leaving as a rate of entropy change just the unconditional term. So basically, the equation that I got for the monitored dynamics goes back to the unconditional case when I turn off my measurement. And this explains also the fact that this information theoretic term depends, very, very strongly and very crucially on the performance and on the nature of the measurement that I'm performing, I'm plugging into my evolution. Great. I'm not explicitly interested or uniquely interested in the rate of entropy change. I'm interested in the rate of entropy production change. And what I'm going to do is to make use of this equation for the rate of change of the entropy to gather information on how the conditional entropy changes, entropy production rate changes in light of the measurement that I'm performing. And what I get in analogy with the expression for, or the equation for the rate of change of entropy is that the entropy production rate resulting from this non-equilibrium process is different from the unconditional case only in light of the occurrence of the presence of this information theoretic term I dot. So the process of acquiring information through the continuous measurement step indeed affects my the rate of entropy production in a way that is entirely quantifiable and entirely ascribable to the nature of the measurement itself. So different measurements result in different processes of information acquisition, and therefore in different ways in which I can steer the non-equilibrium thermodynamics of my system. Now, the standard second law for unconditional dynamics formulated for non-equilibrium processes, whether quantum or classical, read basically as the rate of entropy production in the unconditional case has to be non-negative. When I make use of when I consider a conditional picture, so a picture where I measure the dynamics of my system, this statement gets revised, gets modified, and the bound, so the lower bound to the rate of entropy production becomes I dot. So the conditional term has to be larger, the conditional entropy production has to be larger or equal, no less than the rate of information acquisition that I have through the measurement itself. And while there is no condition on the sign that I dot can take, I dot can be negative or positive depending on the dynamics that I am and the measurement actually that I'm performing. Whenever I dot is positive, this inequality poses a more stringent condition, a more stringent boundary bound to the rate of entropy production, revising, so to say, the Clausius law for quantum systems in the conditional picture. So providing a restated differential and therefore integral second law for the conditional dynamics of non-equilibrium quantum processes. That's great. This is very, very interesting, but there are a couple, at least as far as I'm concerned, but there are a couple of questions that I am naturally led to consider. First, all that is valid in the Gaussian scenario. So the first question that we are going to address is whether or not I can generalize this picture. And the second question is whether these quantities are indeed observable. And while I'm moving to section 2, so to say, to generalize exactly the framework that I have built so far for Gaussian quantum dynamics, in part 3 of the talk, I will present the observability. I will discuss the observability of the quantities that enter that recipe. Okay, how do we generalize the results that I've illustrated for the very specific instance, the very specific system and dynamics that I have presented so far? I'll make use of a collisional approach. So collisional models are incredibly useful, are instrumental for a clear-cut understanding of open system dynamics, and they rely on the following assumption. My system, which is this dark, say, square with an X on it, is affected, so evolves in time, and is affected by an environment consisting of individual particles prepared in a state y of t that interact in a way that is discrete in time, so step by step, discrete time by discrete time. They interact for a short time and with a strength that I can tune, and this interaction I call a collision with my system. They evolve, they change their state, and then in my framework, they are going to be subjected to a measurement. So this is precisely the role of the field in the cavity that I have in the situation that I have illustrated before. So my system is the harmonic oscillator, the quantum harmonic oscillator that I have considered in the previous framework. My environment is basically a discretization of the continuous interaction between my system, between my harmonic oscillator and the field of the cavity, and that is embodied by a series of collisions with suitably prepared discrete systems. And the measurement that I have performed through my general dyne measurement is generalized to a measurement operation described by generalized measurement operator SEM that I perform on the state of the post-interaction, post-collision state of the environment. And these states, say these sub-environmental particles, I will refer to them as ancilla. So they are auxiliary systems that I'm plugging in the dynamics to acquire information on the state of the system and deliver outcomes of measurements. These outcomes are the Z, J quantities that you see in this right-hand side of my slide. And what I'm assuming is that the system X undergoes a series of such conditions. Okay, so there is a number of interactions with different suitably prepared states of the environment, ancillas of the environment, that are all subjected to measurement after the collision with the system. The measurement outcomes, Zj, are collected into a string of measurement outputs, which I call Z of T. And T is the overall window of observation that I'm performing on my system. Okay, so Z, the collection of measurement outcomes, Zj, is the information that I acquire through the measurement that I perform on the ancilla that have collided with my system. Excellent. When I do that, I end up having basically a probability distribution of measurement outcomes. So each measurement is, needless to say, is the result of a quantum measurement that I perform on quantum systems that are interacting and evolving. So I get a probability of achieving a given string Z of T, which comes from the equation that you see on top, at the top of this slide. Okay, so here rho of X, Y1, Y2, Y3, YT is the state, the evolved state of my system and ancilla after T collisions with individual ancillary subsystems. Needless to say, every time I perform a collision, the particle that has, so the ancilla that has interacted with my system is never going to be recycled, is lost, I mean, is subjected to a measurement, but is never fed back into the dynamics. Therefore, I can decide to perform my measurement at the end of the T collisions that I have planned to occur, rather than in a sequential manner. So I can equivalently describe my dynamics as a series of unitary interactions that are then followed by an ensemble of measurements that I perform on the T ancilla that I have plugged in the description of my system, of my process. This rho of xt knowing z of t is the conditional state that results when I'm performing and reading out the measurement that I have performed on the ancilla. And this will be instrumental in the characterization of the thermodynamics and the information thermodynamics resulting from this process. So I need to introduce a couple of quantities. The first is the Holevo information. And the Holevo information is basically the difference between the entropy associated with the state of my system at the end of the process of interaction with the environment, and the conditional entropy that I achieve that means when I instead consider the conditional state of my system. So the state that I achieve when I read out the outcomes of my measurement. What the Holevo information gives me is the information on the system that is contained in the string of measurement outputs Zj. I define also what is called an information, what we call an information rate, which is the difference between the Holevo information at the Tth element, time step of my dynamics, and at time step T minus 1. Okay, so this gives you some sort of differential rate of information acquisition that instead that is quantified by the Holevo information. Now, while the Holevo information is strictly positive, I mean, it takes a couple of lines of calculation to show that, the information rate can take any sign. And this is the key ingredient that I want to exploit, because by being in principle taking an arbitrary sign, my question is whether I can recast this information rate in the form of a balance equation, where I have an information gain that tells me basically how much information I acquire on the state of the system by performing one extra measurement on a Tth element, the Tth element of my environment, and an information loss, and don't worry about the equations, an information loss quantities that instead tells me what is the loss of information, the depletion of the information that I achieve on the system in light of the dynamics that the system itself is performing. Now, these two quantities, G of t and L of t, can indeed be defined. It's a matter of playing a little bit with the algebra of the Holevo information and introducing and taking away, so adding and subtracting two terms to basically recognize that indeed a balance equation like the one that I have at the center of this slide is possible, and I can indeed introduce a gain and a loss term that are strictly related to the rate of change of entropy between conditional states of the system when I perform T-1 measurements and T measurements. Now, the key process, the key result that I get is that the information loss is a non-negative quantity, while G of t can take any value. And that determines the, so to say, the sign of my information rate, delta I of t. Now, what do I want to do with this delta I of t? The first thing that I want to highlight is that if I perform a very large number of collisions that drive my dynamics towards a steady state, then the information rate that I correspondingly achieve declines to 0. So at the steady state, I don't get a non-zero information rate. I stop acquiring basically information on my system at the steady state. So basically performing additional measurements doesn't give me an advantage, but I can achieve that by having an information gain and an information rate and an information loss at the steady state that are individually non-zero. So this means that at the steady state, while the information rate declines to 0, I end up with steady states that allow me to get a continuous information gain and a continuous information loss that balance each other so that delta I infinity becomes 0. In a sense, the measurement that I'm performing allows me to acquire information on the system, and this conspires against the losses that I will get through the natural dynamics, the open dynamics of my system, giving me a steady state that is an informational steady state, is a steady state that is sustained by the process of acquiring information. Antimo, can I go ahead? I heard someone speaking. Is it everything okay?
Yeah, it's good. I mean, it's
okay.
typically 45 minutes plus.
That's okay. I can.
We started a little bit late, so you have
okay.
a few
So
left.
shout when you want me to stop. Okay, so no problem.
That's okay.
Okay, perfect. So we are basically witnessing how measurement sustains an informational steady state, and this allows me to formulate an inequality that will show how the relation between conditional and unconditional entropy production is in that I have presented in the case of Gaussian states and dynamics is indeed a general result. In fact, what I'm interested in doing is looking at the rate of change of entropy that results by performing yet an extra measurement, and this is S of x of t minus s of x of t minus 1, and relay that to the entropy production rate, delta sigma, trajectory by trajectory, so to say, and the information flux. And the equation that you see on the left-hand side of the slide, so this equation here, is what I will get in the unconditional case. For the conditional case, I conjecture a similar relation that this time takes or is built on top of the conditional rate, the conditional state of my system. And that involves a rate of conditional entropy production and a rate of conditional entropy flux, delta phi. These quantities are in general unrelated to each other. And my goal is now demonstrate that indeed they are related and they allow me to establish a relation akin to the one that I've illustrated for the Gaussian state and scenario. And the key consideration is that conditioning on the outcomes of a measurement is a subjective action. I can decide whether or not I should read the outcomes of my measurement. This means that de facto, the process of measuring or not measuring the outcomes of reading or not reading the outcomes of my measurement should have no influences on the flux of entropy that leaves my system and enters the environment. So basically, my claim is that the flux of entropy into the ancilla from the system should not be affected by whether or not I read the outcomes of my measurement. This allows me to state that the rate of entropy flux in the conditional and unconditional case should be the same. Now, these intuitive consideration can be made mathematically rigorous, and indeed the identity between these two quantities can be proven mathematically, and this is what we do in the PRX quantum paper that is mentioned at the bottom of this slide. If I take this assumption, I mean, it's not an assumption, if I make use of this result, then I can establish a relation between the entropy production after T collisions in the conditional and unconditional case that is indeed related to the information rate, the information gain rate that I've introduced in a couple of slides before. So the equation that relates information theoretic quantities to the change between conditional and unconditional entropy production is valid regardless of your assumption, regardless of the nature of your dynamics, and regardless of the Gaussian nature of the process that I have assumed in the first part of the talk. Okay, I get into the last bit of the presentation, so I just need a couple more minutes to explain that these quantities are not only theoretically appealing, but also experimentally observable. This is what we have done with the group of Albert Schließer in Copenhagen by addressing the dynamics of an optomechanical system, probed by and pumped by an external laser field, and probed by an homodyne measurement, connected, so acquiring weak information in a continuous manner on the dynamics of my system. So what you see here on the left-hand side, so to say, in panel C of this slide, is basically a picture in phase space of the dynamics of the mechanical oscillator. The mechanical oscillator is initially prepared in a state that is at equilibrium with the environment of the unperturbed dynamics. So it's a thermal state, basically at the temperature of the environment, which I take out of equilibrium by pumping the cavity with an external laser field, and by measuring the signal leaking out of the cavity, driving the state of my mechanical oscillator in phase space to a new equilibrium state that is a conditional steady state, an informational steady state, being again a quasi-equilibrium state. So it's again a state that is very much close to a thermal state, but at a temperature that is different from that of the environment. So I will be moved to a non-equilibrium steady state of my mechanical oscillator with a variance that is strongly reduced, that is, let's say, reduced by my process of acquiring information on the state of the system. I can formalize the dynamics of this system, of this process, through the equation of motion for the variance, actually the covariances and the first moments of my harmonic oscillator. And I'm not going into the details of the experiment, more than happy to discuss them in the question and answer session if possible. But what I want to stress is that I can characterize basically analytically the terms entering my balance equation between conditional and unconditional thermodynamical quantities and entropy production. As I stated, the steady state of the unconditional dynamics is of the conditional dynamics is a thermal state at a temperature that is not the same as that of the environment, while the steady state of the unconditional dynamics is a non-equilibrium steady state with a temperature very close to that of the equilibrium. This allows us to claim that basically the unconditional entropy production rate is a constant quantity that is fully determined by the parameters of my dynamics. So it depends on the rate of dissipation of my mechanical oscillator, the unconditional variance of position of my state, the number of excitation in the environment, and the rate basically of quantum back action induced by the measurement itself. The entropy production rate at the unconditional level is thus a constant that allows me to identify basically the rate of entropy production in the conditional case with the informational term that entered my revised second law in the conditional dynamical version, modulo a constant that is exactly the unconditional entropy production rate. So this makes my entropy production rate at the conditional level fully observable and indeed reconstructable. It can be reconstructed through standard experimental techniques that these guys in Copenhagen have available. In particular, what they can do is reconstruct the entropy production rate and entropy production flux trajectory by trajectory. And these two plots show what happens to the entropy production rate and the flux in a few trajectories of the dynamics undergone by my mechanical oscillator. And the dark blue lines that you see in the upper and lower panel are the averages. So the average that you achieve by taking the ensemble average over all the trajectories that have been monitored by the experimentalists. This allows you to gather information on the entropy on the informational term and therefore the conditional entropy production, and seeing that the effect of measuring the state of the system indeed leads you towards a state, a steady state at the end, where the informational steady state, the informational term declines to zero, so is depleted to zero, while you achieve a gain that is non-zero and that tells you it's constant, and that tells you that at the steady state, basically, you don't gain any additional information on the state of the system, simply because you have achieved this informational steady state where you balance gain and losses exactly along the lines of what I've illustrated in the previous slide. Okay, with that, I'm done. Let me just show you, say, a recent, but not that recent, picture of the group in Belfast that suffers my tantrums, and acknowledge the guys that are putting the bread on our table, and thank you for your patience and attention. And I'm more than happy to take your question if there is any. Thank you so much.
Thank you very much, Mauro, for the talk.
Really, thank you for a great talk. And so I'm a condensed matter theorist, but I was really intrigued by all of this. So it was really pedagogical as we asked. So thanks for, for doing it.
Thank you for your patience, guys. Thank you.
No, it was super nice. So I would just, just tell you a little bit how it works with the questions.
Yeah.
So if people are on Zoom, they can either write the question in the chat, or they can just unmute themselves and ask directly the question. If people are watching this on YouTube, you can just write this in the chat on the right hand side, and then I will read the question, and then I stop and I leave it to Angelo.
So Antimo, you tell me if there are questions anywhere. I want to ask you, Mauro, a couple of questions. Can you go back to your slides, please, and to the beginning of when you introduce the deterministic and stochastic part, when you introduce the continuous measurement. It's just to understand that one exactly. So the stochastic term is the measurement, but I think that eta should appear also in the deterministic part. Am I correct, or a continuous measurement?
Yeah. It's embedded in my D, so to say.
Okay, so because you called it unmonitored, so there is a part.
Sure. If you want, okay, so probably a better description should be deterministic and stochastic.
Okay. Just to be on the same page. So thank you. And then the thing that I don't understand might be a very silly question is why the covariance matrix doesn't depend on the noise?
Does not depend on the noise. It does depend on the noise.
It does depend, the covariance matrix. Okay, misunderstood you then.
It does depend on the noise, but it does it in a special manner. So it depends on the noise without being stochastic in nature.
Okay, no, then I rephrase my question. Why doesn't it depend on the stochastic term?
It's a feature. It's a bit of magic coming from the Gaussian nature of the Gaussian nature of the dynamics and measurement, Angelo. It comes. I don't have a better answer. It comes from the calculation. And as far as I'm concerned, is a bug or a feature of the Gaussian nature of the dynamics.
But it contains Q squared and P squared, right? The covariance.
And the covariance matrix covariance matrix contains only P squared and so it contains P squared, Q squared, and PX and QP.
Yeah. Okay.
PQ and QP. Yeah. And this is it's an old result that comes also from old papers by Doherty and Wiseman on the dynamics of on conditional dynamics. These review here, so this paper by Genoni, Lamy, and Serafini digs into that in quite a bit of detail.
Okay.
Thank you, Andrea, for your question. Thanks.
Thank you, Mauro.
Okay, so there are no questions on YouTube. So if people who are watching this on Zoom can ask, they want to ask a question, they can just unmute themselves and go for it.
So if there's none, I have a last question for Mauro, but this is a tricky one, if you wish, since so that goes back to my field of research. So in one of the initial slides, you mentioned that your heart is in the quantum to classical transition. So the question would be, what is your take on that, let's say?
Okay. So my take is that we have an additional tool. So we have an extra tool in the toolbox of instruments that you can make use of to characterize the transition from quantum to classical. So what we are seeing, and these are very preliminary results that the community is gathering, is that when you move to many-body quantum systems affected by so performing an open system dynamics, and for say the feature, the characteristic, the dynamics of the entropy production in many-body quantum systems is indeed extremely sensitive to whether you have quantum features in the state of the system or not. So the behavior of entropy production in a many-body system affected by decoherence is strikingly depending on whether or not your system, you can characterize your system as fully classical or not, or deviating entirely from fully classical. By fully classical here, my definition of fully classical is a state that has, for instance, no quantum coherence in the density matrix. So it seems that while other indicator of non-classicality are smoothened by features like temperature and so on, by decoherence, the entropy production seems to have a sharp difference left and right-hand side of the quantum to classical transition. So my hope is that you have a sharper tool that allows you to pinpoint the transition from quantum to classical in a way that other figure of merit can't. And this is still a debate. I mean, an open question. I mean, we don't have clear-cut evidences that this is the case, but it seems to be playing a big role in whether or not the system is fully quantum or fully classical. At the end of the day, irreversible entropy production is basically a statement on micro reversibility. So you break micro reversibility, and therefore you have a surgence of entropy production. So it has to be related to the nature of the dynamics that occur and the non-classicality of the state that you are dealing with.
Okay, thank you.
It's the topic of years of, I hope, years of research to come.
I can see that.
Okay. So if there are no further questions, I think we can thank Mauro for the great talk, for the patience of actually delivering the talk for us tonight. Thanks everyone for joining, and the next talk will be in a month from now. The speaker is still pending. But it will be the last Wednesday of April. This is going to be the next event.
Thank you very much for hosting me. Thank you so much. And
thank you, Mauro, for having accepted. Actually.
Thank you, Mauro.
Hi. Bye. Thanks. Bye.
Bye. Bye. Bye. Ciao.